Thank you to everybody who's joining us, either this morning or this afternoon, depending on where you are in the world. I'm very pleased to be joined today by Dan Hallow of Bristol-Myers Squibb for today's guest webinar on the application of DynoChem reaction modeling to quality by design.
Our development of the mechanistic model, which is really where the heart of where DynoChem was employed, our design space selection and verification process, some conclusions, and then I'll wrap it up with some common questions that we received as we have presented this in a number of different forums. So the first topic that I'd like to introduce is that this work was really focused on the control of a critical impurity in the penultimate step of the synthetic sequence. This impurity I'll refer to as impurity C, and it was deemed critical as this impurity can carry over into the API step and thereby have the potential to impact the drug substance quality. So essentially what we have here is a cross between a series and parallel reaction where the sodium methoxide is reacting with not only the substrate A, but it can also further react with intermediate B. On the right there is shown the rate laws for these elementary steps, the first being an equilibrium involving actually two reactions, the second being the first order reaction of the transient intermediate to the product, and then the ethanolysis reaction. So these differential equations are the basis for our mechanistic modeling going forward. The first, we performed a risk assessment for the reaction parameters to develop some appropriate assumptions, and I'll get into that in a little bit, but basically deciding which parameters were important to model, which ones did we want to hold at conservative values, and how we would approach it to define our final design space. Next, we wanted to define the mechanism and reaction rate kinetics, and then this is often the most difficult part for any mechanistic modeling. Often the reaction mechanism is much more complicated than the reaction rates we have here, so this is often a very complicated step. Next, develop the mechanistic model to predict the impurity levels across the multivariate space, so regressing those model parameters and eventually getting us to the predictive model that we want. Next, we sought to define the design space based on guidance from the mechanistic model, and this was really done by using the model to understand the potential contours of failure, to develop appropriate parameter ranges, and a final verification strategy. And lastly, we verified the design space via some experimental testing. This shows the 12 model building experiments with regard to the impurity formation. The circles are showing the HPLC data points, the actual measurements, and then the solid line is showing the model prediction for all those model building experiments. And you can see that the model did quite well in predicting the impurity level, even with regard to changes in the temperature. Wherever you see that inflection point, that's where we change the temperature set point to a reduced temperature. So talk a little bit more here on the error. We did perform some assessment of the predictive capability of the model. We compared the errors between a model building set and a separate verification set. DynoChem was utilized, there's a design space exploration tool, and DynoChem was utilized to simulate numerous experiments, approximately 80 experiments, to develop some response surfaces for the model plots. Shown here is on the x-axis is these net sodium methoxide equivalents, and on the y-axis is the temperature. The top graph is the substrate concentration, and then down below is the impurity formation at a given reaction age. The important thing to realize is that at high base and high temperature, we can reduce the residual substrate, and at low base and low temperature, we reduce the impurity formation. So there's some sort of balance that's going to have to be considered in defining our design space to ensure reaction completion, and also to ensure that we don't have too high of an impurity level. Impurity level is shown there on the red. The main contour is where does the impurity level reach 1.76, and the green line is showing the residual substrate concentration, and here we're really concerned about what is the IPC specification where we deem the reaction is complete, and that's at 0.5 RAP. So down below the green line, we are not going to meet our IPC. Above the red line, we're going to exceed our impurity specification. And in the middle there is going to be really where we want to operate between the red and the green line. So one important thing to note here is that the substrate contour is not really quality impacting due to we have this IPC control. So in terms of the design space presentation, we would only show it with the contour of the impurity level at the quench. So just some conclusions in terms of the DynoChem utilization. The fitting tool was used to fit the kinetic parameters for the 4 reactions, and it's used to model and predict the impurity profile. The simulator was used to understand the effect of the different process parameters, so understanding the effect of base, temperature, time, and solvent composition. And this was not only valuable for defining the design space, but we also were able to make some suggestions to improve the process. So suggesting a new temperature profile that I described before, where we reduce the temperature set point to decrease the impurity formation, and this allowed us to increase the process robustness. So next, I wanted to highlight some common questions that we have received through the presentation of this work and the numerous forums that I discussed earlier.